This is why 26 dot breaks your NLP model. Split on spaces, and the period glues to the number. Same age. Brand new vocabulary word. In the next few minutes, we turn that trap into a full words into numbers pipeline. Computers do not read the way people do. They need numbers. This video is about the architecture that turns human language into something a machine can compute. On screen, you see a blueprint metaphor. A sentence about Thomas Jefferson enters a processing engine, comes out as digital encoding, and lands on a kind of memory drum. That is the whole story in one picture. Words go inch. Structured numbers come out. Over the next slides, we will unpack tokenization, clean up vectors, and the models that score meaning from those numbers. Hold this picture in mind. Language is soft and messy. Machines want hard edges, bits, counts, and vectors. Everything that follows is just careful machinery for that translation. Think of natural language processing as a lossy factory line. Raw text is messy. Step 1 chops the sentence into tokens. Step 2 sieves out noise with normalization. Step 3 packages remaining words into vectors, lists of numbers a model can multiply. Step 4 is the evaluator, machine learning that reads those vectors and produces an output like a sentiment dial. The key idea is trade-offs. Every stage throws away some human nuance so the math can run. That is why we say the translation is lossy, useful, but never a perfect copy of thought. The simplest first cut is splitting on Whitespace. Call split on a sentence, and you get a list of chunks. It feels done until punctuation appears. Look at the magnified token, 26 with a period glued on. To a person, that period ends the sentence. To a vocabulary builder, 26 dot is a different word from 26 with no period. That tiny glue problem creates duplicate tokens, broken numbers, and weird features later. Whitespace split is a teaching tool, not a production tokenizer. Here is the trap in code. We assign the Jefferson sentence, call split, and print the last token. You do not get a clean 26. You get 26 followed by a period as part of the string. That is why real pipelines use smarter tokenizers before any counting or modeling begins. Different tokenizers make different bets. Naive split keeps was not and the smiley as single tokens, punctuation and all. A blunt regex that treats punctuation as separators can shatter was not into pieces and erase the emoticon entirely. NLTK treebank follows grammar-aware rules. Was and N''T become separate tokens, while the smile can survive. Casual tokenize is tuned for social media, so contractions and emoticons often stay intact. There is no universal winner. You choose the tokenizer that matches your text, news, code comments, tweets, or reviews. Tokenization is the first blade. Cut too soft and punctuation sticks. Cut too hard and you shred meaning. The right chop depends on the language you actually feed the machine. Single words lose phrase meaning. Ice and cream are different ideas. Ice cream is one. N-grams fix that with a sliding window. On a bigram pass, the window grabs Thomas Jefferson, then Jefferson began building, and so on. Each pair is a packet that preserves local order. Unigrams are cheap. Bigrams and trigrams restore some context at the cost of a larger vocabulary. Use them when word order nearby matters more than raw word counts alone. See the difference? Separate cubes are lonely words. One fused scoop is a phrase. N-grams are how we keep ice cream from becoming ice plus cream. Stop words are the little connectors, a, and, the, of, at. Filtering them shrinks the feature space. NLTK lists about 153 English stop words. Scikit-learn lists about 318. That reduction helps bag of words models, but it is a trade-off. Strip too hard, and you destroy relational context. Suzanne reported, as the CEO to the board, can collapse into reported CEO board. For topic search, that may be fine. For nuance, roles, and negation, keep more of the glue. The Sieve throws out glue words and keeps content capsules. Smaller bags, faster math, and sometimes a quieter sentence than the one a human meant. Stemming is aggressive compression. It chops endings by spelling rules so housing and houses collapse toward a shared stem. The scrap bin fills with ing, ease, and similar leftovers. The final token may not be a real dictionary word. Whose is acceptable if every related form maps there. Stemming is fast and blind. It cares about letter patterns, not meaning. That speed is why classic search indexes loved stemmers, even when the stems look ugly. Stemming is a chop shop for endings. Ugly stems are fine if related words land in the same bucket. A tiny regex sketch shows the attitude of stemming. Match a word, peel a trailing S when the rule says so, return whatever trunk remains. Production stemmers like Porter are more careful, but the philosophy is the same, shared tokens from spelling rules, not from a dictionary of true roots. Lemmatization aims for semantic compression. Picture better, best, and goodness growing from one root, good. A Porter stemmer is fast and rule-based. It may leave better unchanged. A WordNet Lemmatizer is slower, looks up a dictionary, and usually wants a part of speech tag. Feed it better as an adjective, and it can return good. Choose stemming when you need speed and rough grouping. Choose lemmatization when you need real dictionary forms and can afford the extra context. Now the scale problem. Imagine 3,000 books, each with about 3,500 sentences, 15 words per sentence. Track every sequence against a million token vocabulary, and the matrix explodes. On the order of 157 million rows times 1 million columns, around 20 terabytes of RAM in the cartoon math on screen. Without normalization and smarter representations, perfect recall of every sequence is impractical. We compress text toward its mathematical essence and accept that we will not store everything. Hot vectors are the music box version of words. Columns are vocabulary entries. Rows are positions in the sentence. At each step, exactly one column is hot, a 1, and the rest are 0. Play the ones in order, and you rebuild. Thomas Jefferson began building Monticello at the age of 26. Order is perfect. The matrix is also massively sparse. That sparsity is honest and expensive, which is why we soon collapse toward bag of words and denser embeddings. One pin at a time. Perfect order. Mostly empty space. That is one hot encoding, honest, sparse, and hungry for memory. Bag of words presses the piano chord. Instead of playing notes one after another, you smash all keys at once. Word order, the melody disappears. What remains is frequency, the harmonic essence. Storage gets efficient because a dictionary can ignore the millions of absent zeros and only store counts for words that appeared. For many classifiers, that chord is enough. For tasks that need sequence, you will outgrow bag of words later. All keys at once. No melody, just the chord of which words showed up. That is bag of words in one image. Once sentences are vectors, similarity becomes arithmetic. The dot product counts overlapping tokens. If two sentence vectors both have a 1 for Monticello, that dimension contributes 1 times 1 equals 1. Dimensions where only one sentence has the word contribute 0. A score of 1 means exactly one shared packet of meaning in this simplified picture. That same vector math overlap, cosine ranking, is the ancestor of classic search scoring. Rule-based sentiment, like VADER, scores text with a handcrafted lexicon. A smile might add about +2. Great might add about +3.1. Screwed up subtracts. Feed glowing review text, and the engine swings toward +0.94. Feed a harsh review, and you get something like -0.87. The limitation is real, roughly 7,500 fixed words and human heuristics. Unrecognized jargon breaks the dial. Rules are clear and fast until the language drifts. Rules push the needle. Positive phrases swing right. Negative phrases swing left. Fast, readable, and brittle when the lexicon has never seen your slang. Machine learning learns the weights instead. Take about 10,600 labeled movie reviews, turn them into bag of words vectors, and train a multinomial naive Bayes model over tens of thousands of unique tokens. It estimates how probable each token is under each label. On the chart, a random guess sits near mean absolute error 4. After learning token probabilities, error falls to about 2.4, roughly doubling accuracy in this example by counting smarter, not by writing more hand rules. Put the pipeline together. Raw text enters. A tokenizer, even a regex blade, cuts tokens. A normalizer sieve stop words, and a lemmatizer maps began toward begin. A dictionary press vectorizes into bag of words. A model such as naive Bayes scores the vector. A gauge reports a sentiment prediction. Human meaning, stripped of chaos, digitized into space, and scored by probability. That is the classic words into numbers architecture, the foundation modern embeddings and transformers still stand on.